Okay, this video I'm going to talk about Young's double slit experiment and just give you sort of a brief background as to what he did, why he did it, and why it's significant scientifically. I'm also going to follow this video up with a couple videos. The second video will be the derivation of the relationship between wavelength and the geometries used in the experiment, and then the third will be a few examples that show how we can work with numbers in this experiment. So first things off first. The idea here was that he was trying to determine if light was a particle and if light was a wave. So in a most basic sense, we have to think about what particles do and what waves do. So particles collide with one another. So if we have two particles and they try to occupy the same point in space, when they run into each other, they will bang off of each other and go their separate ways. So they collide and fly away. Alternatively, when two pieces of a wave try to occupy the same point in space, so they're sort of waving along till they get to this point here, x, then what happens is, at this point, the waves interfere. That means that the resultant wave is the sum of the two waves. So they either bang off each other or they combine. Here, if one wave was up and the other wave was up, we'd get a very up wave. If one wave was up and the other wave was down, we'd get no wave. We call this constructive interference. And we call this destructive interference. This constructs a bigger wave, and this destroys the wave. So, if the particles run into each other, hit and bounce off each other, they're particles, and they have collisions according to the law of conservation of mass, of momentum. And if they're waves, we get a resultant wave, an interference, a linear sum of the actual wave disturbance at that point. It's actually a direct sum. So if this one was 1 and this one was 1 high, this one would be 2 high. And if this one was 1 and this one was -1, that's how we get an addition to 0. Okay, so that's what waves and particles do when they try to occupy the same point in space. Now, at this point in history, to understand the importance of this experiment, there were a number of scientists on either side of the debate. People thought that light must be a wave or a particle, and it had been used to, both ideas had been used to explain the various properties of light. So, for example, Newton said, since light passes a spot and leaves a distinct sharp shadow, it's not illustrating any diffraction like we would expect for a wave coming into that same barrier, where we'd see the wave curve a little bit. Sorry, that's bad. Try that again. Comes in, but around the barrier it actually curves a little bit. Still no good. Coming in, and then it would curve like that. So then as the wave went out, you'd get a shadow here that wasn't sharp but was instead fuzzy, because the wave is spreading out as it goes around the barrier, so it wasn't diffracting. So what that means then is that the wave wasn't showing one of our main wave or the light wasn't showing one of our main wave properties, diffraction. So based on that sharp shadow, Newton thought that light was a particle.
We found some.
So that's one of the reasons why Newton thought that light would be a particle. Another example why he thought it would be a particle was that light gets to us through the vacuum of space. So if we imagine the sun and the earth very far away, then light rays from the sun get all the way to the earth. Now waves, since they're a disturbance in a medium, needs some sort of medium to conduct them from one location to another location. And since space is a vacuum, there's no medium. And so light getting to us through the vacuum of space just would be impossible if it was a wave. It needs some sort of medium. So that's the second reason why Newton thought light was a particle. Not just Newton and a bunch of other scientists, but obviously he's the big name that we'll recognize from other things. So but there was another side to this argument. And that side was people like Haugen. I'm going to misspell this guy's name. Something like that. I don't know if that Y is there or not. Haugen? Something like this. Anyways, I'm not sure how to spell this name. But he said that if the wavelength of light was very short, we wouldn't see the diffraction. And if we consider wave-like properties, we get things like water waves that show refraction and other things that we see with light. So he believed that light was a wave. The most fundamental different property that we typically associate with waves and particles is what happens when they try to occupy the same point in space. That's why I started with that. Particles collide and waves interfere. So Young decided to do an experiment where he would talk about, or where he would try to see what happened when light occupied the same point in space. And he thought he wanted to see if he could see light interfering. The problem is that most interference patterns you'd observe with light would be proportional to the wavelength of the light. And as Haugen said, the wavelength should be very small. So he needed to create a situation where he had two openings that were small, but also were very, very close together. The distance between the two openings had to be very small. And he also needed a coherent light source. Recall from previous that coherent means same wavelength and same phase. So coming up with a coherent light source, again in the time when this is done, was very difficult. Now we could simply use a laser and we would get a coherent light source right away. And because we have that ability, this experiment is actually much simpler now. So the idea here was that if you shined a beam of light on these two openings, and then we have a screen back here, we should see different things if light collides with itself or if it interferes with itself. If it's like a baseball flying through this opening, like a particle, we should see a bright spot right here where a bunch of those baseballs that represent light collide, and we should see a bright spot here associated with baseballs going through the bottom hole. And that's all we should see. This is if light was a particle. Alternatively, if light was a wave, we shouldn't see the two bright spots offset like that, but instead, just like two sources sitting on the top of a pond, the waves should come out and diffract out of here and travel to the screen. Now, when they travel to the screen, what we see should depend on the path length that the light has to travel from source 1 and source 2 to the screen. If L1 is the same as L2, or if L2 minus L1 is 0, then when those two coherent sources get to that point in space, they should be in phase with each other. They should be lined up. And so we should get a large bright spot here. On either side of the bright spot, there should be a point where the L2 minus L1, or the path length difference, works out to be half of a wavelength. So this would be bright. And in that spot, we should get a dark location. So this would be the n equals 1 antinodal point. And this would be the n equals 1, and this is the n equals 1 nodal point. After having gone through that section where the path length difference is half of a wavelength, we should get a point to points again where the path length difference works out not to be 0, but to be an integer wavelength. What that means is that one wave would have gone one wavelength further, but because of the repetition of waves, they would be back in phase with each other moving forward from these 2 points. What that means then is that we would get a lot of constructive interference and another bright spot. This would be the n equals 2 antinodal point. And again, going further off on our screen, L2 minus L1, getting it to a point where the path length difference is 3/2 of a wavelength, we should get back out of phase with each other and have another dark spot where the n equals 2 nodal point. And then one more time, L2 minus L1. Now we get up to 2 wavelengths of difference, and we get another bright spot, the n equals 3 antinodal point. So dark, light, dark, dark, light, dark, n equals 2, n equals 2, n equals 3, n equals 3, n equals 4, and so on. And so we should get this pattern of alternating bright, dark, bright, dark, bright, and so on, which is obviously very different from the idea of those 2 spots where the baseballs would have hit. So what happened? Well, when he managed to do the experiment, he discovered that he saw these fringes. These bright spots are sometimes called fringes. He saw this interference pattern that we discussed here. And so, from Young's double slit experiment, the idea that light was a wave whose wavelength was too small to see diffraction. Was the conclusion. Now, we still had the problem of the idea of this wave getting through space. And so for a brief period in time, and this is sort of an interesting thing, sort of a mistake in science, we made up something that could exist in space, and we called it ether. And the idea was that this would be the medium for a light wave in space. But we don't get too distracted by this concept, because later it was proven not to be true. But it's just sort of a funny, interesting idea that they got this evidence that light was a wave, and so they had to sort of make up a medium for it. And we sort of made a scientific mistake trying to make something up that we didn't have any evidence for, and later we found out that we didn't need. So that's what his experiment was, using a coherent light source to determine if you'd see an interference pattern or if you'd see collision. Seeing the interference pattern lended support to what was sort of an ongoing scientific debate that to determine whether or not light would be a wave or a particle. And since interference versus collision is sort of such a fundamental idea in terms of what makes something a particle or a wave, for the time being, light was thought of as a wave. We'll come back to this idea and get further evidence later, but for now, light will be a wave, and that's what the scientific community thought.